I'm Dr. Jacob Schrum, an associate professor of computer science.
I'm Dr. Cody Crosby. I'm an assistant professor in the physics department.
And we work together on a project involving evolutionary computation and model rockets. And it really started when Dr. Crosby invited me to an event that he does pretty much every semester with his intro to engineering students.
Yeah. So my introduction to engineering class is extremely broad. It's open to all students from all majors, all years. And so as a result, we really focus on rapid prototyping. And I found that one very effective module to do this is to make model rockets. So the students design and 3D print the nose cones, they laser cut the fins, and they build these really cool model rockets about this size and launch them. One problem that we found is that this design space is really huge. There's almost an infinite number of nose cones and fin configurations that work, and my students would get bogged down in this from time to time.
What really piqued my interest is when I found out that his students used a simulator to test out their rocket designs before they actually physically built them and tested them. Because I work in the computer realm, I'm thinking like, oh, you have a simulator that tells you how these rockets are performing. I could use that and apply some of my artificial intelligence techniques to it. And so I do evolutionary computation. It's one form of AI. The idea is that we're simulating a population of individuals using principles of natural selection, survival of the fittest, but also I focus on a particular brand or type of evolutionary computation that is called quality diversity optimization. And so we want to get a broad collection of different high-performing examples in design space. And so I thought, well, we could use evolutionary computation to design rockets and then evaluate them using this simulator called OpenRocket.
It's completely open source, free to use, and it's used by rocket enthusiasts really all over the world in order to design and model their model rockets. So it's made it very easy to feed these simulation parameters into, and then we can evaluate them extremely rapidly. I mean, we would evaluate thousands, hundreds of thousands, millions of outcomes, and then narrow it down to a few dozen rockets that we really wanted to test and model. And that's where we brought in one of my previous students, Cade Townsend. He was in the physics department and he had an interest in aerospace. So we tasked him with basically doing the design and build of this.
There was a matter of deciding which rockets we were going to create because, as was mentioned, we're creating thousands of rockets. We could easily create many more than that. And so we had to have some sort of structured way of organizing and evaluating, what's worth building. This rocket simulator software supports different types of nose cones. And so we wanted to see if we could get a variety of rockets that have different nose cones, reach different altitude targets, and have different degrees of stability. We focused on one, and then we looked at the altitude heights we were achieving, and we wanted to pick representative rockets that were hitting certain altitude targets and that had different types of nose cones and that were derived from different algorithms. So we're basically testing out a variety of designs, but also comparing the different algorithms to see which one produces better designs and which ones cover the space of possible designs better.
And it's part of my responsibility to really evaluate these outcomes because being an AI algorithm, it doesn't really know per se what a conventional rocket looks like. And some of these designs had very long tapered fins, elongated nose cones, things that were maybe impractical for us to really rapidly prototype on our 3D printer and our laser cutter. So once we had this kind of set of designs, we cut it down further and said, okay, can we actually build it? And as Dr. Schrum just mentioned, is this thing going to be stable? And by stability, we basically mean, is there enough surface area towards the back and weight towards the front? You can think very much when a rocket launches, it's very much like throwing an arrow. If you attempt to throw an arrow backwards so that the feathers are forward, as soon as you throw it, it's naturally going to want to rotate back so that the mass is towards the front. And so with a rocket, the problem is if it ever tries to rotate, it just tends to spin out and then become a pretty significant hazard to spectators. So we wanted to make sure that when we built these, that it would be very safe and that we'd be able to evaluate these fairly. And that way we could also get an altitude for them, because if the flight was not stable, we wouldn't get an apogee or maximum height. And so we wouldn't be able to compare it to the models that Dr. Schrum was running.
We were trying to push the limit a little bit about what qualified as a viable rocket design. Because on the one hand, you could just have an evolutionary algorithm that produces a lot of things you've seen before, and that's fine. But we kind of wanted to see well, it proposed this weird thing, and then he looked at it and thought, I mean, I wouldn't design a rocket that way, but I think it might work. And so we tried a few unconventional ones too, because that was the point of the evolutionary discovery process.
And I think it really showed how these two different disciplines could come together, very much in the Southwestern tradition of Paideia, that we had these two ideas that at first looked very separate. You know, the simulation, building, and testing of model rockets, and these evolutionary design algorithms. And typically I'll end up with maybe a couple computer science students in my class at most. It's really, truly a broad sampling from the Southwestern community. But it was really cool to see that these two research objectives, which each of us had really kind of conducted independently, came together in just a very naturally harmonious project that really worked out in the end, and came together, I think, rather quickly, at least as far as research is concerned. We're really hoping we can deploy this algorithm really in the classroom, so my students don't have to sort through these myriad designs. They can narrow it down to just a few choice selections and then build and test these on their own. And it also could inform the larger model rocket community. If you look around at most commercial designs, they're extremely similar, and that's because these are well tested, because they're safe. But if we've shown that, hey, these designs at a glance you might not even want to test are actually pretty stable, it really could allow for a tremendous amount of creativity, and perhaps we'll be seeing, you know, some commercial model rockets that look very different in the future.